Thank you all for coming. So yeah, like Ali said, I'm a particle physicist here at Warwick. And hopefully, by the fact that you've turned up here, you've got some awareness of the fact that there have been some exciting news in particle physics recently coming out of CERN, that neutrinos might be traveling faster than the speed of light. But as we advertised on the poster, this is a general public talk, so I'm not going to assume any knowledge. So I'm going to start off just by introducing particle physics or reintroducing particle physics if you know it already, reminding you where we are with particle physics knowledge and what it's all about, what we're trying to do. I'll then focus a bit more on neutrinos because they're the exciting, interesting particles that are making all the news, and they're also the particles I work with, so they're definitely the most interesting. Before we actually get on to the result of the experiment and how they went about measuring what these neutrinos were up to. So the world around us is made up of many millions of different materials, different molecules, and they all behave in different ways. Some of them are conduct electricity, some of them won't, some of them are hard, some of them are soft, some of them are red, some of them are green. And this is a bit of a problem if you want to try and design a new device. You want to understand what that material is going to do before you put it in there. And also from a scientific point of view, it doesn't really make sense that there's all this plethora of different things that behave in different ways. We want to make sense of why they do that. And so after centuries of scientific work, it was discovered that all these millions of things were actually made up of just a few elements, just over 100 elements. And they're arranged here in the periodic table, which you're all familiar with from GCSE science. And so it turns out that all these different behaviors, all these different materials can be explained by the elements which make them up, and they determine how they behave. As we study these elements in more detail, we discover that there are patterns in these elements and how they behave as well. And we can arrange them in the periodic table, in this grid-like structure, according to how they behave similarly to each other. So, for example, all the elements in this column here at the end react very violently with water, whereas all the elements in this column at this end, they hardly react at all. They're all very inert. At first, this structure seems like it makes it easier for us to group the elements together and to remember them all, but actually it's a hint that underneath these elements is a simpler physics that's causing this structure to behave, to emerge. And about the turn of the last century, we discovered that actually these elements are all different examples of an atom. An atom is composed of a central core nucleus built up of protons and neutrons. And around that are a cloud of electrons which sort of orbit this central nucleus. Now, the different elements all correspond to just the different number of protons in that nucleus. And every time you get a new element, all you've done is add another proton into this nucleus. And the number of electrons which orbit it determine how that element behaves, how that element reacts with the others. So actually, all 100 or more elements in the periodic table and all of the ways in which they behave are all due to three particles, the proton, the neutron, and the electron. And that's much better. That's much more how we like it as physicists. We like simple things that cause all the exciting and different behavior that we see in the world. There's actually a fourth particle in this image called the neutrino. So not all of the elements of the periodic table are stable. Not all of them hang around forever. What some of them will do is they'll decay into others. So for example, in this instance, one of the neutrons in this nucleus has decayed into a proton to make a different atom. And then out of it has come an electron, but also this green particle, which is a neutrino. We don't really see neutrinos in real life because they travel through almost anything. The average neutrino will travel through a light year of lead before it does anything, before it stops. And so we very rarely encounter these in real life because they just don't interact with our world. Hardly ever. And it seems that these four building blocks then can explain everything that we've discussed already before. Except that it doesn't quite end there. Protons and neutrons, it turns out, aren't the only particles of their type. If we create high enough energy collisions, if we smash things together hard enough, we can make more particles like them. And these particles, again, have a pattern of how they behave. And so we start to get the impression that, once again, there's another level underneath that explains how these different things behave. And indeed, when we look inside the proton, what we discover is that it's actually made up of three particles, which we call quarks. Quarks have a very strange name. In the proton, we call them the up and the down quark. And a proton is made up of two up quarks and a down quark. In the neutron, it's made up of one up quark and two down quarks. And so now this is the fundamental, this is the most basic level of particles that explain all of the materials, all of the elements, all of the atoms that we've looked at so far. There's the up and the down quark, which makes up the protons and neutrons. There's the electron, and there's the neutrino that goes with it, the electron neutrino. And that explains everything that you'll ever use in your life. Everything you'll ever touch, encounter, is made up of these four particles. There are more of them. Another two sets, in fact. But it's not more complicated. This is still staying about as simple because each of these columns is absolutely identical to each other in every way of any importance. The only difference is that each column gets heavier. The mass of these particles increases. So the muon is absolutely like an electron in every possible way. It's absolutely identical in every way you can measure, except that it's heavier. It's about 200 times heavier. And the tau is exactly like the muon and the electron, except that's heavier by another 1,000 times or more still. Likewise, the charm and the top strange named quarks are exactly like the up quark, they're just a lot heavier. And so what we've got here is a repeating pattern. And there's 3 lots of them. If you can't remember all the quarks names, don't worry, because this is the last time we're going to see them. And I've said this is almost all. This is all the matter in the universe. Even no matter how high energy you get, how hard you collide things together, you can't make any matter other than these particles. But there are also antimatter particles to go with them. So every particle we know in particle physics has an antimatter counterpart, which again is absolutely identical to the matter counterpart. It's just that its electric charge is opposite, basically. And now this really is everything that in all the matter particles in the universe. And that's what everything's made of. Those are all the things that we can produce. How they behave is governed by the forces of physics. And there are 4 forces in physics. There's gravity, the one we're most familiar with, that holds us onto the Earth. Electromagnetism, which is the combined, explains magnetism and explains electricity. We've got the strong nuclear force, which is what holds protons and neutrons together inside the nucleus and holds quarks together inside those to form the protons and neutrons. And then finally, there's the weak nuclear force. All this does is, in anything we'll ever encounter, is make atoms decay. So the radioactive decay we saw earlier, which made the neutrino, that would have been caused by the weak force. I'm going to grey out gravity for 2 reasons. One is that it doesn't fit in with our current theory of particle physics. We can't make it go in with the others. And that's something we really like to solve. But the other reason is it's really, really weak. Compared to these other forces, it's a piddly little force that can hardly do anything. If gravity disappeared tomorrow, it would be the end of the world. But your particles probably wouldn't care. They wouldn't notice. Their world would carry on. Their lives would carry on. So that's where we are in particle physics. Those are all the particles we know. Those are all the forces we know that cause them to behave. But the only ones which are important to us today are the neutrinos, the 3 neutrinos, the electron neutrino, the muon neutrino, and the tau neutrino. Neutrinos are all around us, actually. Despite the fact we hardly ever see them, despite the fact they hardly ever interact with us, they're the most common matter particle in the universe. And they come from any interaction, any nuclear interaction. So, for example, the nuclear fusion that goes on in the center of the sun produces billions of neutrinos all the time. There are 100 billion neutrinos passing through your body every single second, which is a bit of a big number. It's a bit difficult to get your head around that, right? 100 billion of them every single second, and you've never noticed them. That's because most of them go through you, and even if one did stop, it would stop in such a weak way that you wouldn't notice it. It wouldn't make any difference to you at all. And 100 billion isn't all of the neutrinos that are going through you. There are also neutrinos produced in the upper atmosphere. High-energy cosmic ray particles traveling through space eventually crash into the Earth. They smash into the atmosphere, and they produce exotic, short-lived particles which decay to, amongst other things, neutrinos. And those neutrinos travel all the way through the atmosphere, and they go through you as well. They'll probably go through the Earth and out the other side as well. Supernova also produce neutrinos. So 1987 was a very momentous year in physics for 2 reasons. The first is it was the year I was born. And the second is that it was the first time since mankind had invented the telescope that a supernova occurred close enough for us to see. And you can just about see it in the center here, that blue dot with rings around it. That's the supernova after it happened. And those rings are just all the stuff that's been thrown off the outside of it. The other reason this supernova was particularly interesting was because it happened not just since humanity invented the telescope, but also since humanity had invented the neutrino detector. In fact, there were 3 operating in the world at the time, in Russia, America, and Japan, and they detected the neutrinos coming from this supernova, as well as the telescopes detecting the light from it. Like I said, neutrinos are produced in any nuclear reactions, including those we make ourselves, for example, at nuclear power stations, like this one called Chaux in the south of France. And finally, we can make our own neutrinos deliberately for the only purpose of making neutrinos at particle accelerators, like the Large Hadron Collider at CERN, like this one in Japan, which is the one I work at. It's called J-Park. It's based on the east coast of Japan. That's not a good place to build particle accelerators. They don't like magnitude 9 earthquakes, which is why it's not running right at the minute. But when it is running, what it does is it has a circular ring. You take protons and you accelerate them around that ring, and you accelerate them faster and faster to higher and higher energy. Once you've done that, you smash them into a target. All of particle physics basically amounts to smashing high-energy things into other things. We're basically the thugs of physics. And what you do is you smash these protons into a target. Just like when high-energy cosmic rays hit the atmosphere, they make a shower of exotic particles, so too when these protons hit the target, they make a shower of particles. They're short-lived exotic particles called pions and kaons, but the important thing is they don't hang around long. They decay to, amongst other things, neutrinos, and in the particular case of this experiment, muon neutrinos. So why would we bother to make neutrinos? There are problems in particle physics. Despite the rosy image I painted earlier of all these particles we know and all these forces we know, there are still holes in our theories, still problems to be solved. One of them is about matter and antimatter. Physics treats matter and antimatter the same, or it should do in our theories. So if you make a particle of matter, you should also make a particle of antimatter at the same time. If you want to destroy a particle of matter, you have to destroy a particle of antimatter as well. So you always have to have equal amounts of matter and antimatter. No particle interaction is excluded from that rule, including the biggest particle interaction of all, the Big Bang at the start of the universe, which was basically an eruption of energy in particles. But because it should obey the laws of physics like everything else, we think it should have made matter and antimatter in equal amounts. But when we look out into the universe, everything that we see is made of matter. There's no antimatter left. All the stars, all the galaxies, they're all made of matter. There's no antimatter. And so somehow physics is treating matter and antimatter differently. It's disposing of some of that antimatter when it shouldn't have done, unless it disposed of matter. The particles that we think could be explaining this are neutrinos. We think that it's possible that neutrinos and antineutrinos are treated differently. In order to figure out how, we need to investigate something called neutrino oscillations. Neutrino oscillations basically amounts to, at one end you make muon neutrinos, and then by the time it's traveled through the Earth, it's changed into a different type of neutrino. So at J-Park, at this accelerator on the east coast of Japan, we make these muon neutrinos, and we put them down into the ground about 1 or 2 degrees. And then because the Earth is curved, they come back out the other side 300 kilometers later. We've made muon neutrinos at the start, and what we hope is to find that they've changed into electron neutrinos by the other end. And we have a near detector at the start. It's a very cleverly named detector. It's near the start, so we call it the near detector. It's a very important detector because here at Warwick, we helped build some of it, and that's what I spent my first year doing, was building some of those grey blocks in that diagram at the top. And we used that to measure how many muon neutrinos we had in the start, and then we measure how many electron neutrinos we had at the end at this far detector, Super Kamiokande. It's a great Japanese name for a detector. It's basically a 50 kiloton tank of water. And when neutrinos interact in this water, they create a flash of light. Okay? And so what you see, all these dots around this beautiful detector, all these dots are light sensors, basically. They're about this big, but they're light sensors nonetheless, and all they do is look for light coming from neutrinos. But T2K isn't the only neutrino oscillation experiment. there are 3 different types of neutrinos, and in order to figure out whether they can be treated, matter and antimatter neutrinos can be treated differently, we need to measure all the different types of oscillations that can occur. So the name of the game is to build an experiment for every type of neutrino changing into every other type of neutrino, pretty much. And so here's a list of experiments, and here's the neutrino changes they're looking for. Sometimes they're looking for a neutrino changing into a different type. Sometimes they'll just look to see how many of the type they had in the first place are left over at the end. Here's T2K. We're looking for muon neutrinos changing to electron neutrinos. And then there's the other experiment, the opera experiment, which wasn't actually out to measure how fast neutrinos were traveling. It was actually here to do neutrino oscillations, and it was going to look for muon neutrinos changing into tau neutrinos. But as physicists, what we're always trying to do is break the laws of physics, find out where we've been wrong before, because that's when things get interesting. So while you're at it, while you have this beam of neutrinos traveling a very long distance, you can try and measure how fast they're going. You thoroughly expect to measure that they're traveling less than the speed of light because that's what they're allowed to do. But the reason all these people packed into a lecture theatre at CERN a couple of months ago is because the guy in black up the front here is about to tell them that they didn't measure these neutrinos traveling slower than the speed of light like everyone expected, but in fact faster than the speed of light, which is not allowed. So what I want to do now is just go through how they did that, how you can possibly measure things traveling as fast as something as the speed of light, before we worry about what happens when they do. So just like T2K, they use proton beam to make some neutrinos. The experiment starts at CERN, the place where the Large Hadron Collider is built. But the only thing at CERN is not just the Large Hadron Collider. CERN is actually the foremost particle physics laboratory in the world, and other things go on there too. In particular, this experiment. So here, this grey tube running through here, that's the Large Hadron Collider, that's their tunnel. And the tunnel at the top, the grey one running along the top, that's the smaller proton accelerator which feeds them into the Large Hadron Collider. You start them off at a slow speed, and then you put them into a bigger one to boost them to a higher speed. And so you can see the feed tube where it comes through for the Large Hadron Collider. But that's not the interesting bit. The interesting bit is the blue tube, where it takes these protons away, and just like at T2K, they smash them into the target. You make the exotic short-lived pions and kaons and send them down a tube where they decay into, amongst other things, muon neutrinos, which are shown in this diagram as these little white dots coming out at the end. Neutrinos aren't white or dotty, but still. And then, just like in T2K, you point it down into the ground. And just like T2K, because the Earth's curved, it comes back out the other side, 730 kilometers away in central Italy, at a laboratory called Gran Sasso. Gran Sasso is built into a mountain because the world isn't the nice place that we think it is. It's full of radiation. There's radiation coming from things from space, all the things around us. And if we build our detector inside a mountain, then we can shield ourselves from some of that stuff, which would otherwise get into our detector and look like the things that we really wanted to see, even though we don't want to see them. Inside that mountain is this detector, the Opera detector. It's not a water tank like the one at T2K, but nonetheless what it's still doing is detecting light that comes off the particles when neutrinos arrive, when neutrinos stop in there. And most of them go through, but occasionally one does see them. And we've got to use this setup now to measure how fast neutrinos are traveling. What do we need to measure the speed of something? Everyone should be familiar with this equation. If you want speed, you need the distance and you need the time, okay? Let's start with the distance, and then we'll worry about the time later. Distance is a pretty simple thing to measure if you're on the surface of the Earth. Hopefully you're all familiar with GPS. In fact, many of you may have used it to get here today, so you know it works. And if you place a receiver on the surface at CERN and at Gran Sasso, GPS is accurate enough to pinpoint those locations to an accuracy of about 2 centimeters, which is pretty accurate enough to produce this graph. And there's sort of 3 interesting things in this graph. The first is that it shows you that GPS is very good at positioning you on the surface of the Earth, but it's not very good at getting your altitude. That's why the graph at the top, the up measurement, the altitude, is really jittery, but the graphs below, the east and the north, the position on the surface, are very good. So good, in fact, that in this area where the red box has been drawn around, you can see the effects of the 2009 earthquake in L'Aquila, which is just down the road from Gran Sasso, which shifted the entire thing by 5 centimeters in both the north and east directions. That's pretty impressive to see that sort of movement. What's even more impressive is the slant that you can see on this graph. That's continental drift. You can see the entire continent moving here. That's how accurately you can position things on the surface. And that's great for CERN. At CERN, which is the world's foremost particle laboratory, you need to know where all your accelerators are very, very accurately. They've spent a lot of money and a lot of time positioning those things and measuring them, their positions, to millimeter accuracy. So taking your position on the surface and figuring out where your neutrinos start relative to that is pretty easy. You know it as well as you know the position on the surface. But that's harder at Gran Sasso because we're inside a mountain. In order to get to that lab, you need to travel down a tunnel, a very narrow tunnel with 2 lanes of traffic going down it. So if you want to take your GPS signal from outside and get it inside, you need to close off one of those lanes and inconvenience a load of Italians. And you use prisms and lasers to transfer that position from your GPS receivers on either end of the tunnel down into the center of the lab. This is a 10-kilometer tunnel, so that's a very difficult thing to do, and it's not a straight tunnel, it's a curving tunnel. And that whole process of working in such a confined space, because they only had one lane, gave them an uncertainty of 20 centimeters, which is much larger than the 2 centimeters we had before. They could probably do better, but they'd have to close both lanes, and that really would inconvenience the Italians. But there we go. We can measure the distance from when the neutrinos are made in CERN to where they finish in Gran Sasso as just over 731 kilometers to an accuracy of 20 centimeters, which is pretty good. So now we need to figure out the time it takes for the neutrinos to travel. Before we can actually time the neutrinos, we need the clocks at CERN and Gran Sasso to agree with each other, which is not as simple as you might think. The first thing you might think to do if you want your clocks at CERN and Gran Sasso to agree with each other is to use GPS. GPS doesn't just send out the position of the satellites, it also sends out their times. The problem is that that time can be affected a lot as the signal travels. So there is a region of the atmosphere called the ionosphere where radiation from the sun has knocked all the electrons off their atoms, and that interferes with the radio wave coming from the satellite and can slow it down or speed it up. The size of that ionosphere changes during the day and night, winter and summer, or any host of things. And so it's very difficult to get that right. And then finally, the electronics which receives the GPS signal is not very good either. Well, relatively not very good. It has a lot of jitter on it. And so the accuracy of the timing agreement in the clocks between CERN and Gran Sasso can only be done to about 100 nanoseconds. Here you can see the jitter that you get off one of those clocks. So what we need these clocks to agree with each other so that we can time this properly. So for example, if I was going to travel to my grand's house and I wanted to know how long it took me to get there, I could look at the clock in my living room to see what time I started, drive there, and then look at the clock in her living room to see what time I got there. And the difference between those times would be the time that I traveled, how long it took me to get there, as long as those two clocks agree. If my grand's clock is slow by 10 minutes, it will appear like I've traveled 10 minutes faster than I really have. So if we're going to measure those neutrinos, we need those clocks to agree. And so what you do is you buy a very, very expensive cesium clock. In fact, you buy 2 of them. You put one at CERN, and you put one at Gran Sasso, and you use that to correct the time that you got from the satellites. Cesium clocks are very, very good, very, very accurate clocks. They're one of the most accurate clocks in the world for 2 reasons. The first is that they're very, very reliable. If you kept a cesium clock running for 1 million years, it wouldn't even lose a second. And the second reason is they're so reliable that we actually use cesium clocks to define what a second is. So you can be sure that this cesium clock is going to tell you what a second is because that's what we use to define a second. So now we know we can agree the times at our GPS receivers at either end. But that's not we need to get that time now into the beamline to where the neutrinos are made and into the detector where they're detected. And that's not very simple if you need to know things down to the nanosecond. Because nanoseconds are a very short time. You need to worry about how long it takes that signal to get down there. This very complicated diagram is the one they produced to show what this involves at Gran Sasso. Basically, the orange blocks amount to the GPS time being received and comparing it to the cesium clock. So at the orange blocks, we have our original time, and we need to then send it down to where the neutrinos are being detected. So, for example, the 8.3 kilometer optical fiber that takes the signal from the GPS receiver down the tunnel to the laboratory, it takes 40,000 nanoseconds for that signal to get down there. They had to measure that. They've also had to measure the time it takes for the signals to get through all the electronics near the detector. When a neutrino makes light in your detector and you use a light sensor to pick that up, it takes time for the light to get down the detector to the sensor, and it then takes time for that sensor to be read by some electronics. And you have to account for that too. It takes 60 nanoseconds for the light to get out of the detector. And you have to add all these things up. Some of them increase the time, some of them decrease the time. And you have to put that all together, otherwise you're going to be completely off. And you have to do it both at CERN and you have to do it at Gran Sasso. And you better not make any mistakes, because if you do, this can have a big effect. But nonetheless, they were able to do it, and so the clocks in CERN and Gran Sasso are in agreement to an accuracy of 2 nanoseconds. They will never, we reckon they'd never disagree by more than 2 nanoseconds, which is very impressive for two things in different countries. But after going to all that effort of 2 nanoseconds, there's another problem. We now we know what time it is on either end. We know what distance it is on either end. It's time to measure how long it takes the neutrinos to travel. But there's an added complication. When we make neutrinos, we do it by slamming a bunch of protons into a target, and out at the other end come a bunch of neutrinos. That bunch of protons is 10.5 microseconds long. So that's 10,000 times larger than the accuracy that we've just put all that effort into determining the clocks at either end. And it gets worse. What you see, most of those billions of neutrinos will travel straight through Gran Sasso, and all you'll see is probably one, if you're lucky. And you don't know how long it took that one neutrino to get there, because it might have come from the neutrinos right at the start, and it's traveled very, very slowly. It might have come from the neutrinos at the end, which have traveled really fast and caught up. You don't know, for a single neutrino, how long it took that single neutrino to travel. So you need to do it on average. What you do is you take this shape of protons and you assume that after putting those protons into a target, the shape of neutrinos you get out the other end is the same. And so you transfer the shape of neutrinos that you think was there to Gran Sasso. And then you do it multiple times, as many times as you can. So you have your first bunch of neutrinos, and you get one event, and one neutrino interaction, and you take the shape over there. Then you get another one, and you add the shape onto what you already had before. And then you get another one, you add the shape on, and you keep on doing it, and you keep on building up neutrino interactions on the other side, until eventually this is what you get. This is the total data that they took. So at the top here, what you can see, the black dots, that's the data. That's the neutrinos which interacted in the Gran Sasso laboratory. The red line is the adding up of the sum of all of those shapes of protons, of the neutrino bunches that you saw earlier. And so they should match. The red line at the top here is drawn where it would be if neutrinos had traveled at the speed of light. In fact, it looks like they've traveled a bit earlier. So what you do is you allow that shape, that bunch of neutrino shape, to move up and down, and you work out where the best fit is. You do a calculation to work out which position best fits the data, and that's where you get here. And you find that the neutrinos arrived 60 nanoseconds early, which is not very much. That means they're traveling 0.0025% faster than the speed of light, which really doesn't seem like very much. But the speed of light is the upper limit that anything is allowed to travel. Nothing should travel faster than the speed of light. It is completely forbidden in the laws of physics. So it doesn't matter whether it's 0.0025% faster or whether it's 25% faster. It's faster, and it's not allowed to be faster by any amount. So that's still breaking the laws of physics, regardless of how small it's broken the laws. There is one uncertainty here, one possible problem that there could be in this measurement, and that is the assumption that this big bunch of protons, when it gets smashed into the target, still has the same shape and size. That when it comes out of the target as the exotic pions and kaons, it still has the same shape and size, and that when they decay to the neutrinos, it still has the same shape and size. That's an assumption that we've made. we don't really have any good reason to believe that it would be any other way, but still, we can't check it very easily. The only way we can check it is to make those bunches of protons really, really small. You didn't do this in the first place because what you need is you need lots of neutrinos in order to get lots of measurements. But in order to check this, because it's getting serious now, we've made them really, really narrow. We make them 3 nanoseconds wide. And now you can measure the time it takes every neutrino to travel, because this neutrino could only have come from this bunch of protons, this bunch of neutrinos at this time. So when you get a neutrino and you know when it started, you know how long that neutrino took. You're doing a direct measurement. You're not averaging out, you're measuring exactly how long it took that neutrino to travel. And this is what they saw. I'm afraid it's a bit vague because I had to copy it off a paper, but what they see is all these events here. This is how early they've arrived, and they've all still arrived 60 nanoseconds early. We thought we found a problem with it, and when we looked, the neutrinos are still traveling too fast. It hasn't solved it. They're still arriving 60 nanoseconds early. They're still traveling 0.0025% faster than the speed of light. They're still breaking the laws of physics, which they shouldn't be doing, according to this man. He says that they shouldn't be doing it. Albert Einstein, the most famous physicist ever, in 1905, he wrote the theory of special relativity. The theory of special relativity is our law book for everything when they're traveling, anything that's traveling fast, anything that's traveling near the speed of light. And it's the law which most of modern physics is built on top of. Special relativity is built on 2 underlying principles, 2 statements that are believed to be true, and it relies on them. The first is that physics is the same for everyone, for all observers in the universe. Regardless of where they are, regardless of how fast they're traveling or where they're traveling, they all agree on the same physics, that physics is always the same. And it also says that the speed of light is the same for all observers. The speed of light is not just some speed of something traveling through space. The speed of light is part of physics. And if physics is the same for all observers, for everyone, regardless of how fast they're moving, then the speed of light must be the same for everyone, regardless of how fast they're moving. That can seem a bit strange. Excuse me. So, if I were to stand here and to fire a laser away from me, that light would travel away from me at the speed of light, 300 million meters per second. If you were to run past me really, really fast at the same time, you would think that that light would get away from you at the speed of light minus the speed that you're traveling, because you're chasing after it. You would think that it would be getting away slower, but it's not. Because the speed of light relative to you is always the same. You will always measure the light going away at the same speed, which is pretty strange, right? If I'm standing here and it's going away from me at 300 million meters per second, and you're running past me after it, and it's still getting away at 300 million meters per second, that's really strange, really difficult to get your head around. The reason special relativity gets away with it is because it's the speed of light that's important, not the distance or the time of the measurement. So if I were to hold out my arm and I could measure it, I would get whatever measurement. But if you were running past at half the speed of light and you looked at my arm, it would look a lot shorter to you than it does to me. I'm not wearing a watch, but if I was, it would look to me like it's ticking at the rate of 1 second every second. But if you travel past me at half the speed of light and you were to look at my watch, it would look like it's traveling slow. But that doesn't matter, because distances and times are not important in special relativity. We can disagree, you and I, if you're running past me, you're traveling at a different speed. We can disagree on how long things are, or how far they are, or how long they take. But what we must agree on is the speed of light. And so a consequence of all this is that nothing can go faster than the speed of light. Nothing can catch light, nothing can go faster than it. Everything has an upper limit of the speed of light that it must not go past. The speed of light is not just the speed of light either. We call it the speed of light because the only thing we have that travels that fast is light. But actually, it's not just the speed of the fastest thing we've ever measured, which happens to be light. This speed is a fundamental, central part of the theory. It's part of how it's built. It's part of how it works. So, for example, the most famous equation ever, E equals mc squared, contains the speed of light. What it does is it relates the energy of a particle to its mass times the speed of light squared. So it relates the energy of a particle to its mass. But there's nothing to do with light in there. Light doesn't belong in measuring a particle's energy or a particle's mass. But the speed of light still comes in here because it's not just the speed of which things are traveling, it's the central part of the theory. It's part of the rules of special relativity. And special relativity, since it was written over 100 years ago now, has become the foundation of physics along with quantum mechanics. So special relativity deals with things that are traveling fast, and quantum mechanics is how we deal with things which are very, very small. So if we want to do particle physics, we need small things which are traveling very, very fast. So we combine this, relativity and quantum mechanics, into relativistic quantum mechanics. That's the theory built on top of those two. And on top of that, we build particle physics. On top of special relativity, which deals with things traveling very, very fast at the same speed, you might also want to deal with things which are being accelerated, things which are feeling forces. And that's why 30 years later, Einstein came up with general relativity, which he built on top of special relativity. That's how we deal with gravity across the universe. And then finally, there's astrophysics and cosmology. Astrophysics relies on special relativity because it works by measuring light coming from across the universe, so it really would like it if that light behaved properly. And cosmology rests on all these things. It uses particles, it uses astrophysics, and it uses general relativity to put it all together to try and explain how the universe is working. So it's all built on top of special relativity, which apparently, according to Opera, is broken. We've broken special relativity, it's wrong, and so when you take it away, the whole thing comes tumbling down. That's what's left of physics if you remove special relativity. So this comes as a bit of a surprise, this measurement, because of that. All this work we've been doing for hundreds of years is all built on top of something we thought was right, something we've checked before. So there are experimental surprises as well here, because it's not the first time that we've tried to measure how fast neutrinos are traveling. We've also done it using the supernova 1987A, which I mentioned earlier. Supernovas produce neutrinos. Initially, when the star collapses in on itself, you get a big nuclear reactions and loads of neutrinos come off. And then later, a shock wave is released, which produces the light you see. So the neutrinos leave the star about 3 hours before the light that we see leaves. It then travels millions of light years from the nearby galaxy to us. And the neutrinos then arrived 3 hours earlier than the light. We saw the neutrinos in our detectors, and then 3 hours later, we saw the light arrive from the star. They left 3 hours before, and they arrived about 3 hours before. But if Opera is right, if these neutrinos travel 0.0025% faster than light, they shouldn't have arrived 3 hours earlier. They should have arrived 4 years earlier, which is a bit of a difference. And we know they didn't arrive 4 years earlier. We know they arrived 3 hours earlier because we saw them arrive 3 hours earlier, and 3 hours later, we saw the light arrive. So you've got to, these two results don't agree with each other. And when results don't agree, what you need is another experiment to go away and check it. And so that's what we need now. Opera have done the best job that they can to try and solve all the problems that people have brought up with what they've done, and the result is still there. The neutrinos are still traveling too fast. So we need someone else to verify it. The best way to do that is using another neutrino oscillation experiment. So here's Opera. They fire their neutrinos over a distance of 730 kilometers. The MINOS experiment in America, they fired their neutrinos over a distance of 735 kilometers. And they tried to measure the speed of light as well, but their uncertainties were too large to tell whether neutrinos were traveling faster or slower or not. They couldn't see any effect. But in light of these rather interesting results, they're going to go away and look at their data again and try a little bit harder to get those uncertainties down to see if they can see anything. But unfortunately, MINOS has closed down for now. They've finished, so they're not going to get any more information. The T2K experiment where I work could also do this. We've only got a 300-kilometer distance, though, which the neutrinos are traveling. And if it only is a 60 nanosecond difference for Opera, it's going to be less than 30 nanoseconds early for us, which makes it that little bit harder. It also makes it harder that we don't have cesium clocks at either end. Cesium clocks are expensive, and money is tight. But if these results hang around, no doubt we will try and convince someone to give us that money. And then finally, there's the NOVA experiment, which is what MINOS has been turned into. So it starts at the same place as MINOS, and the detector at the far end is further. It's over 800 kilometers away. No doubt, if this result is still around when they turn on in 3 or 4 years' time, they will try and do this as well. but we've got to wait 3 or 4 years to find that out. So it's really still out there. The results really still stand, that neutrinos still appear to be traveling faster than the speed of light as far as we can tell. So if that's true, if they have done the measurement correctly, if it is traveling faster than the speed of light, how could we possibly explain this? What strange and weird physics is going on to cause this? The first thing physicists usually jump to is extra dimensions. So we live in a universe of 4 dimensions as far as we can tell. There are 3 dimensions of space, and then there's time, the 4th dimension. But in physics, there's nothing to stop you adding a 5th, 6th, 7th, 8th, or whatever in order to make into your calculations to see what effect that has. These extra dimensions need to be small so that we don't notice them normally. You also got to have it so that only neutrinos can go through your extra dimensions, and that's why they're the only things that can travel faster and not light. But nonetheless, there are other problems in physics which use extra dimensions to solve them. So for example, the neutrinos are much lighter than all the other particles. They're a lot lighter than other particles. All the other particles are much heavier. We don't really understand why that is, but maybe if they're hiding some of their mass, some of their energy in this extra dimension, that could explain it maybe. So it's not the only reason you would need extra dimensions to do this. String theory could also solve this problem. Probably because string theory can solve any problem, because it can predict whatever the hell it likes. If you want to use string theory, you can just change a few numbers here, add a dimension there, and add an extra brain or something there in another place, and suddenly you can change your results to fit whatever anyone wants you to fit. And so that's the power of string theory, is that it agrees with everything, but then the problem with string theory is that it agrees with everything, and so you have no idea whether it's right or not. Sterile neutrinos. So the neutrinos we talked about before were the electron neutrino, the muon neutrino, and the tau neutrino. And in neutrino oscillations, they change between those types as they travel. And we see these because when they interact, they produce electrons, they produce muons, and they produce taus. So we can see them. But what happens if we added an extra neutrino, a sterile neutrino that's not able to interact with the world around us, that can't produce any particles? And then let's suppose that that particle can travel faster than the speed of light. So the nice matter ones that we know and love aren't allowed to break the laws of physics, but this one will do. And then as the muon neutrino leaves opera, it will oscillate into the sterile neutrino, travel faster than the speed of light, and then oscillate back into the muon neutrino in time to be detected on the other side. Maybe that sounds a bit strange, but then there are also anomalous measurements in neutrino oscillations, which until recently we assumed would just go away when we did a more careful measurement. But you can also explain those anomalies by introducing sterile neutrinos, and so maybe we could solve 2 problems here at once as well. And then there's the downright wacky, which is what you can find if you go on the internet. So this is the one I found. A theorist suggested that some rare particles were produced in the Big Bang. And they are very long-lived particles, so they're still around after the Big Bang. For some reason, they don't hang around in empty space. They get lodged in planets, and they stick around in planets. And apparently, if you're within 10 meters of one of these particles, you can travel faster than the speed of light for a short period while you're within 10 meters of it, but only if you're a neutrino. And so it's just bad luck that there happens to be one of these hanging around between CERN and Italy. And it speeded up these neutrinos as they went past it to give us our 60 nanoseconds. But there are no of these strange particles between the supernova and us, which is why they arrived on time. Fantastic. Usually, when you start to see a list of caveats like this, you start to get suspicious, and you start to think that maybe this isn't the right way to go about it. And finally, really, anything else could be put in here. Special relativity is our law book. It's our rule book, which tells us what we can and can't do. It tells us what's allowed in physics. And we've just chucked that out the window, and with it, everything else we've done over the last 100 years. So actually, there's not really any limits if neutrinos are traveling faster on what we could use to explain it. But if you do come up with a theory, you've got to do certain things. You've got to predict 60 nanoseconds at opera. You've got to make them travel just the right speed to get the right measurement. You also need to explain why the supernova neutrinos don't travel faster than the speed of light. And in the same way that special relativity, which deals with high speeds, looks the same as Newtonian physics at slow speeds, your theory must also agree with special relativity and Newtonian physics in the areas where we've measured those before, because we have measured those before to be correct over the last 100 years to incredible accuracy. So your theories also got to agree with those in almost every way, other than the fact that they allow neutrinos to travel too fast. Finally, it could just be another 12 meters of cable which someone forgot, because that's all you need to get a 60 nanosecond difference. And so any careless small mistake which any of us could have made could also cause this. So, in summary, this is a very, very difficult measurement to make. The speed of light is incredibly fast, and measuring distances between Italy and Switzerland to centimeters, and measuring times to the accuracy of nanoseconds in two different places is very, very difficult. They've tried their best, they're professional physicists, they know what they're doing, and now the world is checking over what they've done, but it appears that they've done their job right. But nonetheless, with such sensitive things, it's very easy to make a small mistake that's 60 nanoseconds large. Having said that, if this was true, this would be the most exciting, most interesting, most revolutionary discovery in physics in the history of physics. It would change the way we understand the universe, the way we think it works, and it would bring about a new era of us discovering unknown physics that we'd never thought of before. The most important thing is that it's the job of physics to keep on questioning, regardless of how many hundreds of years you've been questioning a theory and checking it and it's right, no matter how many other theories you've built on it, which you love and know, you still question the assumptions at the beginning, because that's when things really get interesting. Thank you for listening.